Okay, so I just gave back the exams. We talked about it a little bit. And we also have a homework assignment due today, right? And I think this was a design exercise. You're going to make some flip-flops using other flip-flops. And I've already helped a few people with questions. But are there any questions that anyone else might have about the homework assignment due today? When you construct an SR from a D, right. So,
I don't know if I did something legal.
okay, let me draw the picture. So the question is how to construct an SR from a D. So what happens is, here's the clock coming into the D, and the D has a Q and a Q bar going out. And since you're constructing an SR flip-flop, here's the question. There's always a combinational circuit here. And because we're constructing an SR out of a D, that means that our input into the combinational circuit will be S and R. And then we will possibly have a feedback here with a Q, right? So if we look at what it is that we're trying to construct, it looks something like this. So this is our external Q and our external Q bar. So if we draw a line around here like this, this looks like an SR flip-flop because we have an S coming in and an R coming in and a Q bar coming out and a clock pulse. But inside we just have this D, which means that this combinational circuit would be how many in, how many out? 3 in, 1 out, which means how many Carnot maps? 1. Yeah, only one Carnot map. And namely, it's the Carnot map for D. And the in, and 3 input means how many cells? 8. So it'll be a little rectangular. And what was your question about whether you did something illegal?
Yeah, so I was making the table where I have QSR, QT.
Oh.
When it's 1, 1.
When it's 1, 1.
I put an X in the QT plus 1.
That's absolutely, the question is, absolutely. Because look, you're trying to make an SR, right? It's undefined what it is when it's 1, 1. So that's a don't care condition. So in your minimization, take advantage of it.
Cool.
That was a good question. Is everybody?
Yeah, my other question is, in my circuits, I drew a line. Can we use the Q bar output?
Absolutely.
Okay.
I only drew this Q feeding back to here, but there's no, it would be wasteful to have the Q coming back and then putting an inverter if you needed the Q bar, because we have it automatically from here. Okay. So even though we analyze it as 3 inputs, it's okay to use the Q bar as another input because it's always just the inverse of Q anyway.
Okay.
So that was good. Those are good questions. Any more? Any other questions? Well, when we do a Carnot map, isn't that minimize the space?
Right, but if we didn't use a Carnot map.
You should always use a Carnot map.
Right.
To do it the most efficient way.
Try to guess.
Well, no, there's times in which I saw that a single exclusive OR.
No, please do not use an exclusive OR.
Okay.
Just do it the way. I mean,
Well,
you know, there are.
I provided both.
Your question?
Even if we use
With the Carnot map.
But what a Carnot map gives you, a Carnot map gives you a minimized and or. Now, if I were, to be strictly, to do this strictly the correct way, we would have to do what? We would have to do a minimized what? And we would also have to do it with the Carnot map, and then we'd also have to minimize an or and then take the one that has the fewer gates. But let's not do XOR because XOR is combinations of ands and ors and inverters. So the XOR?
The XOR, yeah.
Oh, I see.
Yeah, that's why I mean, like,
Yeah,
like
but the-
gates, I did one.
Yeah, but the thing of it is, inside, what's inside of an XOR?
All 3 gates, but then I just did
Well,
one.
yeah. Well, I prefer them to be and/ors. And we have to understand too that, this is not, we're not being strictly thorough in our minimization, because if we were in a real world application where this really made a difference and it wasn't just an exercise, we would have to do both and/or, because they're not necessarily the same, right? It's possible that one might be more minimum than the other. Anyway, did you have a question?
Yeah, for mine, I just use multiplexers, but is it
Multiplexers.
Yeah.
Oh, you mean like we did in the lab?
Well, I mean,
Wait, what do you mean?
Work.
Oh, you guys are doing all these ad hoc techniques. You know, look, I mean, I really, yeah. Here's the thing. I really prefer you really shouldn't do that. In the lab, we saw how to use a multiplexer to implement an arbitrary function, and you could use a multiplexer to do that. But, you know, then the multiplexer has all these gates inside of it.
Yeah.
So, you know, I prefer, you should. You really need to do it using the design process that we outlined with Carnot maps, because we're going to generalize that now. Actually, not today, but next time we meet. We're actually going to generalize that to a general design procedure. And I'd rather have you do the design procedure the way that we will have to continue to do it. You see what I'm saying?
Would you suggest I redo it?
I would.
Okay.
Yeah. Sorry. All right. So everybody, these are all good questions, and you are being very creative, and I admire your creativity. But on the other hand, it'd be much easier for me if you just stick to the standard process. All right. Any more questions? These are all really good questions. Yeah. Yeah, that's because when you transfer the data from the design table to the Carnot map, it's in the same order. It's in the same order as transferring it to the Carnot map.
How come we don't do that on the other stuff then?
Because we weren't transferring it to the Carnot map.
I was just curious.
Well, true. Well, I mean, it's just that in those situations when we know that we're going to transfer the data from the table to a Carnot map,
Then you just
that's when I think it's easier for you to set up the table in the same order as it's going to go into the Carnot map to minimize the errors that you make in copying over. Because, like I say, there's ones and zeros are floating all over the place, and when you start having, that's just a technique that I don't know where I got it. I might have gotten it from somebody else, but
Because I made my true table and then I was checking it with the book, and mine was out of order for the last two.
yeah, well, probably
But it's
because
you switched
it's
over.
yeah, and so that's just a little tip, a little, I don't know, yeah, to minimize errors because it's real easy because
Yeah, that makes sense.
yeah. Now here's the thing: we will do that. That's a technique that I commonly use in design, but not in analysis. Because with analysis, we don't use Carnot maps.
Right.
Carnot maps are a design tool. Carnot maps are not an analysis tool. They're a design tool. So, and in fact, today, so now what'll happen is, today we're going to go back and do it, today we're going to do a big analysis problem, a big sequential analysis problem. All right? So now, let's review then what is analysis versus design. So let's take a look at figure 11.26 and recall, with analysis, what are we given?
Function.
The input
In the circuit.
and the circuit, the sequential circuit. Are you with me? And what do we have to produce when we analyze?
The output.
We have to produce, the output, what happens, as the clock pulse comes by. Are you with me? On the other hand, with design, we are given the input and the what? Yeah, the desired output. And we have to come up with a circuit. Yeah? Is everybody clear? So what we're going to do today is one big analysis problem. And I'll tell you right now what's going to be on the next exam. There's going to be an analysis problem and there's going to be a design problem.
That's it?
Right. Well, there's going to be more than that, but you can be sure, you can count on, you can count on an analysis problem and a design problem. You can just count on that. Are you with me? So let's see how to do analysis. All right. Now, so here's a bullet list, step 1, step 2, step 3 for analysis. But let's skip over here to figure 11.27 and take a look at the circuit that we want to analyze. So let's look here at figure 11.27. And everybody understands now that this circuit, with analysis, this circuit is given. Yeah? Now, what do we have coming? What's the label for our inputs here? What are the labels? What input signals are coming into this?
X1, X2, and clock.
Yeah, X1, X2. Yeah, the clock, we assume that the clock is coming in and going into the clock inputs of all the state registers all simultaneously, right? So when we say input, we don't really count the clock. Are you with me? And how many outputs does this have? Does this circuit have? It has 1, and what is that labeled? Y. Now, this particular flip-flop is being constructed out of what kind of flip-flops are the state registers? They are what kind of flip-flops? T flip-flops. And what does T mean? Toggle. And how does a toggle flip-flop work? If T is what? Is 0, then what happens to the state? It stays the same. But if T is 1, then what does it do? It toggles. All right? Now, here we have a set of 2 registers. Are you with me? So how many possible states are there that this whole system can be in between clock pulses? It could either be what? How many states are there possible for this entire 2 flip-flop system? Yes, 4. Why, what are the 4 states?
Stable and toggle for the first one, and stable and toggle for the second.
Well, when we say the states in between the clock pulse, we're talking about the value of, now do you see that A is the Q output of, but what is this FFA? That's flip-flop A. Are you with me? And then A is the label of the Q output of flip-flop A. Are you with me? And then FFB is flip-flop B, and the capital letter B is the Q output of flip-flop B. So what are the possible here? What are the possible states? The possible states are for AB. How many possible states are there? 0, 0, 0, 1, 1, 0, 1, 1. Those are the 4 possible states. Is everybody with me? Those are the 4 possible states that it can be in. Right? And then for each one of those 4 possible states, what can come from the outside? How many possible input combinations are there? Can we
4.
Yeah, there's 4. Because X1 could be what? X1, X2 could be what? 0, 0, 0, 1, 1, 0, or 1, 1. And for each one of those, the states could be in what? The states could either be what? 0, 0, 0, 1, 1, 0, or 1, 1. So do you understand what we have to do to construct the state transition table?
16.
16. There are 16 possible transitions. Because there's a transition for all possible states, and for each state, all possible input combinations. Is everybody with me? Mm-hmm. And furthermore, do you see that for in between the clock pulses, do you see that A and B will be in some state, and X1 and X2 will have some values, and do you see that this Y is going to depend on that? The output Y is going to depend, because what's coming into Y?
B prime.
B prime, the bar is the same as prime, right? Mm-hmm. So B bar and what?
X1.
And X1. So this y is going to depend on a state and on an input. Is everybody with me on this? Okay. So now, that's the circuit. Oh, and you see that x1 is coming in here to TA, but then it's being ANDed with what? B, all right. And then x2 is coming into an OR gate, right? And then the OR gate, and it's being ORed with what?
A.
Come back here, and we say, oh, that's A, which is the, yeah, right. And then, so that's what the T is going to be. So the question is, how is this thing going to behave? All right, so now here's what, so now with that preview of our circuit, here's what we're going to have to do. And we're going to do all three of these steps today. Step 1, list all possible combinations of current state and current input in an analysis table. How many rows will this have?
16.
16. For each combination, compute the output and the current inputs to the state registers. Are you with me? Because what are we saying? Because what's going to happen is there's going to be a function here in this combinational circuit that's going to determine what goes into the T's. Are you with me? Is everybody clear? Okay. And then step 3, from the characteristic table, now we know the characteristic table of the T flip-flop, right? We just said it.
Yeah.
If it's 0, it's unchanged, 1 toggles, right? So from the characteristic table, determine the next state and construct the state transition construct the state transition table and diagram. Are you with me? Is everybody clear on this? So now we're going to do all three of these steps with this circuit. Now, what was the first one? So here comes a big table. How many rows?
16.
16. And so what do we start with? We start with A at time t, B at time t, and then what? What was our input?
X1.
X1 at time t and X2 at time t. Now, is everybody clear on this? Okay, so now, and so how many possible combinations? We have what? 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, right? Then 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, right? Uh-oh. Do you know that sign called think ahead? Have you seen that sign before? It starts over here. Think ahead. I'm running. Didn't think ahead. I should have done my lines first. And now what's the next one? 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, and then what? 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. And now this. Now let's not peek and see if we can figure out. Now, does everybody see that this is all, so if we look at figure 11.27, this is all possible combinations of inputs and states. Now does everybody see that for each one of these, so here's our first task. Our first task is to determine, here let's go back to our checklist. Our first task is to, list all possible combinations of current state and current input in an analysis table. We did that. Step 2, for each combination, compute the output and the current inputs to the state registers. Now, what's our output? In this particular example, our output is what? It's y. And notice that what we're going to do is we're going to do y at time t. We're not doing y at time t plus 1. Now, this is always something that's a little confusing when we go to do our state transition diagram. Does everybody understand that what we're doing here is we're doing y before the clock pulse makes the transition. Are you with me on this? So let's just remember that. It's y at time t. All right? So we're going to have to do that. And then let's go back to our bullet point. For each combination, compute the output and the what? Current what? Inputs to the state registers. Well, now so what inputs do we have? How did we label the inputs going into the state registers? TA and TB, right? So here, let's do TA at what time? T. And TB at what time? T. Are you with me? So we'll calculate that. Is everybody with me on this? And then, let's go back to our bullet point again. For each combination, compute the output and the current inputs to the state registers, and then step 3, from the characteristic table, determine the what? The next state. So now, how do we organize our table? You guys, just knowing how to write up the table is a big deal. So now what?
Is this step 3?
Yeah, so now for step 3, what will we need in our table for step 3?
We'll have t plus 1.
Which one, but what at time t plus 1?
Why?
Can
No.
you go back?
We're only going to do, yeah, let's go back. You want to go back? Yeah, okay. So this is step 3. From the characteristic table, determine the what?
The next.
The next state, and then construct the state transition table and diagram.
So we're going to need
Is it
A and
A
B
or
at
T
t
plus
plus
1?
1.
Yes,
A and B.
very good. We are going, see here there was A at time t and B at time t. A clock pulse is going to come along and it's going to change the state. So then here what we are going to need is A at time t plus 1 and B at time t plus 1. Okay, now look you guys, every single step of this is easy and mechanical, but I won't give you these headings. You understand what I'm saying? So we just have to understand what analysis is, and we have to be able to figure out what we have to put in the table to do our analysis. Are you with me? So does everybody see what it is that we're doing? How we are analyzing this? Are we good? And notice that we don't do a y at time t plus 1.
That's going to be my question. How come we don't do that?
Is that part of the design?
Because no. It's because when it changes, then after the clock pulse, we don't know what B is going to be. You see what I'm saying? I mean, we would just look at this up for the next state. We would look up. I don't know how to explain this.
Well, because here it's determined what A and B are.
Right. This is a listing. This is a listing for what Y is for every possible combination of this.
Right.
So when the next state comes along, that'll be in another state, and you can always look up what it's going to be at that state.
But we can really predict the next state.
Well, we haven't predicted the next state yet. I mean, it would be redundant. If we did this, then Y at t plus 1 would be just like this, but it would be with, I mean, that wouldn't give us any new information about what Y at, you see what I'm saying? Yeah. But this is always a sticking point. But this is always the way analysis is done. It's always Y at time t. Are you with me? So Y at time t, and then, yeah. All right. Now we're going to go around the room, you guys. All right, and we're going to fill in all these tables. We're going to fill in every one of these things. So here's the circuit, figure 11.27, and here's this. And I tell you what, let's start in the middle, and we'll go this way, this way, this way, and then this. We'll go that way, right? And those of you who are on the camera, you're in on this too. So come back from the future and tell me what this should be. Okay, so now here's what we're going to do. Now tell me, looking at this, what is Y?
X1 and not B.
It's Y is X1 and not B. So what do we have to look at? We have to look at this one. We have to do this and not this. So can you tell me?
0.
We're going to start here. Oh, okay, that's 0, practice. Okay, that one's practice. So it's, wait, what is it? X2, B, wait. It's X, wait, which one is it? It's this one. It's this one and not this one. All right? So it's this one and not this one. Okay, so now we'll go around the room. Okay, so what's this and not this? You can pass if you want. This and not this.
Whose turn is it?
Oh, it's, I was not going to mention names because this is going on, being recorded for posterity. Oh, you did say 0? Okay, so that's 0. Why? Because 0 and 1 is 0. Okay, what? Okay, so this one? 1. Next. 1. Next. 0. Next. 0. 1 and not 1. 0. 0. 0. 0. Good, because 1 and not 0 is 1. This one? 1. This one? 0. This one? 0. This one? Who's next? This and not this. 0. And this one. Who's next? 0. All right. Now, did we have any challenges? I wasn't looking or thinking. So, 0, 0, 1, 1, 0, 0, 0, 0, 0, 0, 1, 1, 0, 0, 0, 0. Are we good? Okay. Now we have to do TA and TB. So what it now? But now this is mechanical. What is TA? It's what? X1 and what? B. So we go here. We just look at here and we go this. So it's, now it's just these two. It's ANDed now, right? Okay, so this should be, now this is less complicated. So we just AND these. So next. 0. Who's next?
0.
0. 0. 0. 0. Next. 0. Now, okay, but look, it's because it's 0 and 1. We're ANDing these. Are you with me on that? Is everybody good? We're ANDing this and this because what we're doing, look, we are calculating what TA is. TA is X1 and B. So we're taking the T1, so we're taking the wait, which one did we just do? Yeah, we're taking, so 0 and 1. So you see how that, okay. Okay, so 0, okay, so next. 1. 1. Who's next? 0. 0. 0. 0. 0. 0. 1. 1. Do you see how to do that? Is everybody clear? We're just, okay. And now what is TB? What's the function? What is the TB function? I mean, how does TB work? It's X2, here's an OR gate, so X2, we follow this around, and it's X2 or A, right? From the circuit, which is given. Are you with me? Analysis, given the circuit. So now with this column, we have to go down and look at what? X2, but it's OR, right? So now we have to look at this column and OR them. Is everybody with me? So let's OR these. So who is next? So what is 0 or 0? 0. Is everybody good? So next. 1. Next. Was it? Let me see. Is it this one?
I'm just having trouble following. So it's A or X.
Yeah. Oh, yeah. Let's go back and recalibrate. Yeah. Okay. So it's X1. TA is X. Oh, sorry. Sorry. TB is X2 or A. So it's this. So it's this column or this column. Are you with me? So this one's 0, and then what? 1. 1, yeah. has to throw off your neighbor. Okay, what was this one? 0, no, 0 or 0, right? Is 0, 1, 0, 1, 3. Did you say 3? Oh, I thought I heard somebody say 3. And now I'm all off. Well, who said this? What's this one? 1. Who's next?
Oh, sorry, 1.
1, 1,
1.
1, 1, 1, 1, 1. Any challenges? All right. Okay. And now, you guys, how the heck do we get this? How do we get A, flip-flop A, at time t plus 1? Well, now we got to use our knowledge about what?
TA.
About the toggle flip-flops, about T flip-flops. And so we have to think, how does the T flip-flop work? Well, here we have the input to the flip-flop, right? And we also have, and what else do we need to know? What A itself is, right? So now the fact that this is 0 means this does what?
Nothing.
Does not change. Now, does everybody understand how we do this? We put one finger on this column and one finger on this column and say, if this is the input of the T flip-flop and this is the state, then what's the next state? Is everybody clear on how to determine that?
Yeah.
Now, this isn't just gates. This is how we use our knowledge of the characteristic table of the T flip-flop. Okay, so this A is what? Wait, who is next? Okay. 0. That would still be 0. Why? Because the state is 0 and the input is 0 here. So it stays the same. And here? 0. And here?
Oh, 0.
And here? 0.
0.
0. Now, this is an interesting one. Why is this one 1? Because it's going to toggle, this state is 0, and it's going to toggle to 1. So this state changes, right? Okay, and now what? And now this one? 1. And now this one? Okay. Next? Who's next? Okay.
It's also 1 still.
Yes. And okay. Good. 1. 1.
Oh, 1.
Now,
Wait.
let me see. Yeah, let's make sure. Hold on. What did you said 1, right? Okay. 1. 1.
0.
0. 0. Because why? Because this one toggle. You guys got something going there? Okay, so okay, so now what do we do? We look at what? We look at the current input and this state. And so now what does this do?
It'll be someone else's turn.
0.
0. 1.
0.
0.
0. Wait.
No, it's
it's
wrong.
1.
Oh, okay, you want to take it back?
Looking at the wrong one.
Okay. So this, now, wait, you said this now is 1 because it's going to toggle this state. Is everybody with me? This is going to toggle this state. So this is going to toggle from 0 to 1. Okay, next. 1. 1. Oh, challenge.
Oh, sorry, it's already.
Wait. Okay, so, okay, so now, are we good for this? Because what's it going to do? Oh, wait.
It's going to toggle. Because
It's going to toggle which state? 1. So this is going to toggle this state. Is everybody good? So 0, okay. 1, 1.
No.
Oh, challenge. Uh, B,
TV is 1.
the input to the flip-flop is 1, to the T flip-flop is 1, and the current, oh yeah, 0.
1.
1.
We need to ask the people out there in camera land. 0, 0,
Zero.
are we good? Okay, let's check our work. Figure 11.28. Can somebody please verify that?
Verified.
Already? All those columns? Are you serious?
Yeah.
You got all these columns? You got that? Oh, I mean, the first 4 are trivial, but, all right, 0, 1, 1. 0, 1. That was pretty good. Okay, so now what I'm going to do is, since this table is up on our slide, after we did all this work, and now, going back to our bullet list, what do we have to do? So we constructed this, from the characteristic state, we determined the next state, so now what do we have to construct? The what? State transition table and diagram. So, how do we do a state transition table? Because how many possible states are there? How many possible states are there in this system with 2 flip-flops, with 2 state registers? How many possible states are there?
16. Oh, 4.
4. Are you with me? So our state transition diagram is going to have 4 states.
Cool.
Are you with me?
I'm with you.
And we're going to construct that from a state transition table. Is everybody clear on the state transition table? So in the state transition table, you remember how those of you who are in computer systems, we just did state transition tables. What a coincidence. Do you remember how state transition tables work? It's A at time t, B at time t, and what are the possible states? 0, 0, 0, 1, 1, whoops, 1, 0, 1, 1. Is everybody with me on this? Okay. And what do we have? And then what do we? What always goes here? Which state? In a state transition table, what goes here? In the body of the state transition table, what goes here? The next state. Are you with me? The next state goes here. And what does the next state depend on? If we're in this state and we have a certain input, it tells you what the next state is going to be, right? So how many possible inputs do we have?
4.
We have 4. And what are those possible inputs?
0, 0,
0, 0.
1, 0, 1, 1.
Right. Right. So we're going to label this x1. Here we're going to call this x1 at time t, x2 at time t. And those 4 possibilities are 0, 0, 0, 1, 1, 0, 1, 1. Is everybody with me on this? Like this, okay? And now what we're going to do here, in the body of the table, we're going to indicate what's in the body of the table here. What is going to be here is going to be A at time t plus 1. Now watch this. It's A at time t plus 1, B at time t plus 1, comma, Y at what time?
T.
Y at time t. Now does everybody see that? Are you with me on this? So here we go. Let me see, which way should we do this? If we're in state 0, 0, and we have a 0, 0, the question is, what state do we go to? All right, so who was last? Okay, somebody identify yourself. Who's next? You're next?
Yeah.
Okay, so if we're in state 0, 0, and we have a 0, 0, what state do we go to next?
0, 0.
We go to 0, 0, and the input at this time before the transition
0.
is 0. Now, can you read that off of figure 11.28? Does everybody see where he read that off of? You still? Okay, let's look. So how did you do that? If we're in state what?
0, 0.
0, 0, and we have what?
0, 0.
0, 0 for the input, where do we go?
0, 0.
State 0, 0 over here. Now, are you with me on that? So this is the state, this is the input, this is the next state. So we're just reading it off the table. And furthermore, y at time t
0.
is 0. And so we'll separate that with a comma. Are you with me?
I got this. 0, 0.
Okay, so now the pattern, so now let's stay in the same row here. Okay, so 0, 0, comma what?
No, isn't it 0, 1?
Oh, I thought you said 0,
No,
0.
I was saying. I'm saying for AB 0, 0, and then for that one 0, 1. It's
Oh, I see. Okay, so don't say, just say what goes
0,
here.
1, comma
0, 1, comma what?
0.
0. Now, is everybody, any challenges?
Well, what's the second 0 for?
The second 0 is y at time t, which we get from that column right there. Are we good? Okay, so next. 0, 0, comma 1. Next. 0, 1, comma 1. I detect a little tentativeness here. So is everybody checking?
Yeah. I got the same thing.
Okay, good. Okay, so here. Who's next?
0, 1, comma 0.
0, 1, comma 0. Is that 0, 1, comma 0? Or is it 0, 1, comma 0? Just kidding. Okay, and next.
0, 0, comma 0.
0, 0, comma 0.
1, 1, comma 0.
1, 1, comma 0. Who's next? Oh, you want pass? Okay. Okay, hold on. Well, go ahead. Go ahead.
1, 0, comma 0.
1, 0, comma 0. Okay, so now, do you see how we're getting this? What state are we in?
0, 1.
We're in 0, 1. So we come down here to where AB is 0, 1, and x1, x2 is 1, 1. So do you see that's this row right here? 0, 1, and then 1, 1. And then we're just and the next state is 1, 0. Are you with me there?
Yeah.
So on that row. And then the current y is 0. So this is 1, 0, and 0. Is everybody good with this? Okay, next.
1, 1, 0.
1, 1, comma 0.
1, 1, 0.
1, 1, comma 0.
1, 1, 1.
1, 1, comma 1.
1,
1, 1, comma 1. Who's next? Sorry, again? 1, 0, comma 0, is that what you said? Are we good?
Yes.
Okay, next.
1, 0, comma 0.
1, 0, comma 0.
0, 0, comma 0.
0, 0, comma 0. 0, 0, comma what? 0. All right. Let's see. Is that, let's check with figure 11.29. Did we do it right? Come on, do your instant analysis here. Okay, now we've got to go on. Sorry, but we can't start in the middle next time. So we're going to go over just a few more minutes. 0, 0, 0, 1, 1, 0, 1, 1. All right? So this is the state transition table. This is going to be the state transition diagram. All right? Now, let's just do each one of these. But now what we're going to do here is we have to be careful here. It's going to be slash. Because look, if we're in state 0, 0, and we get a 0, 0, what do we go back to?
0, 0.
We go back to itself. So this is 0, 0, but look. We go back to 0, 0, but this is going to be, it's not going to be, I'll tell you what let's do. Let's start next time. Let's finish this up next time. So we'll start right here and I'd hate to keep you over. All right. See you on Monday, I guess it is, right?